Welcome to OS2 Workshop 4 on sampling rate and length. So this workshop uses the results and scripts from Workshop 3. So first of all, before you start this worksheet, then you should make sure you have completed all the steps in Workshop 3 and have available the data and that you downloaded, and also the scripts available in your workspace. So if we look at the worksheet, Workshop 4 is entitled Sampling Rate and Length. So we are going to be exploring changing the sampling length and sampling intervals on the tidal time series that you looked at in Workshop 3. So that is the aim, to explore the effect of changing the sampling length and the sampling interval. So in other words, we're looking at a continuous variable which has been sampled already, and we truncated the time series to the year that you're looking at, 2012, and it has already been sampled at discrete intervals, but we're going to explore changing both the length and the interval and see what effects that gives us, because it will determine what variabilities that we can see, what periodic components we'll be able to observe. Okay, so step 1 is to load the BODC tidal time series from 2012 using your scripts and data from Workshop 3, and then we'll just plot the data up just to make sure it looks right. Okay, so open up a MATLAB window. I've already got mine here, and I've already loaded in the tidal data from Workshop 3, so you can see that I've labelled the structure Tide 2012. You can see in my workspace over here. So just so you don't have to sit there and wait for it to load on the video. And you can see that I'm in my OS202 Workshop 4 folder, which has the scripts loading the tidal data and plotting the tidal data here, as well as the source data. Okay, so it's now in my workspace, so we'll work from there. Just to check that we know that we've got the right data and that looks correct. This is the script for plotting it, so you should have this available as well in your workspace, or at least in your path, so it will run effectively in your command window. So this is a function, and we need to pass it the variable or the structure name for the tide data. Okay, so let's just get rid of that, and then we want to plot tide data, and then I have called it Tide 2012. Okay, just bring that down a bit. Okay, so that looks fine. Okay, big gap in the middle, but that should look familiar to everybody. Good, so it's there. Now, before we continue, I'm going to reassign the time axis to T, so we don't have to type it out every time. Tide 2012 dot T, and also the tidal height I'm going to assign to H. There we go, just makes it a bit shorter for typing it out. So these variables, you've already seen these. H, the tidal height, is given in meters, so that's the correct units there, and the time is actually in days, although we didn't see that on the x-axis in the graph. Okay, so I think that's step 1 done. So now we need to go to our worksheet again, step 2. So consider the time axis. So we're just going to explore our time series. I think we probably know the length of it already, but we don't know how many samples are in that time series, and we don't know the time interval between those samples. So both the length and the time interval will determine both the shortest and the longest observable periods in our time series. And it might just be useful to refresh ourselves by having a quick look at the slides from the lecture looking at sampling rate. And you can see a periodic signal here. And the sampling interval, so this could be mimicking our tidal time series as an example. And you can see here that the sampling, or the time between samples, is just adequate such that we could pick up this periodic component. Okay? Now, if it was shifted by a fraction of the wave period, then you might imagine that you were sampling it at slightly closer to the equilibrium value. However, this really represents the kind of the lowest sampling rate that you could possibly use to pick up this sample, because we're just picking up the peaks and the troughs here, okay? And if we were to sample any less regularly, then we wouldn't be able to observe that component. And we can have there's another example here on sampling rate, and whereby we look at, so if this was our tidal time series and we sampled it at the intervals shown by the squares, then you can see if these were the times that you just took your observations, then when you joined them up, you wouldn't see any fluctuation whatsoever. If we sampled where we have the little circles, then you just pick it up, okay? And ideally what we'd like to have is more samples than that. So more samples per wave period, okay? So we go back to this slide again, then you can see that our sampling interval, okay, should be less than half of our sampling period, okay? So that means that we will not be able to resolve any signal that has a period which is less than twice this interval here. So in general, we want to be oversampling. Okay, so given this information here, then what we need to find out is what is the sample interval, delta t, in our time series, our tidal time series, okay? So let's just minimize that as well. Okay, so going back to our MATLAB command window, what we want to know is what is the sampling interval. So in other words, what is the time between samples, or delta t. So let's call that del t, and we could choose any two time samples or time indices. So t2, and subtract the one that occurs before it. Okay, so these are just sequential markers of time, and we want to know what that is. Okay, that is 0.0104, and I believe that is a measurement of time in days. So 0.0104 days between each sample. If you wanted to just do a little check, we could choose any other two time indices and check the difference between the two. Okay, so let's try, I don't know, 67 minus t at 66. So what that means is that we are looking at the difference in the time stamp between the 67th sample and the 66th sample, and that should be the same as between any other two consecutive samples. And indeed it is, so that's just reassuring. Okay, now because 0.0104 days is not very easy to imagine what that means, let's just convert that to minutes. So let's multiply del T by 24 hours per day times 60 minutes per hour, and ta-da, we get 15, so 15 minutes. So that means the time interval between each of the samples in our tidal time series is 15 minutes. They were sampled every 15 minutes. This means that the shortest observable period must be twice this. In other words, the shortest observable period must be 30 minutes. Okay, I don't know how to write that out here. We don't really, at the moment we're just kind of exploring our time series to understand what the data is at the moment, okay? And we will try and change this later. So the shortest observable time period must be twice this, which is 30 minutes. So in other words, we need to get a minimum of 2 samples within a cycle in order to observe that cycle. Okay, so we've got the sampling interval. Let's find out what the sample rate is then. So we call that Fs, and Fs is equal to 1 over delta t, and I think we've got that in the PowerPoint slide somewhere. This one, oh, it's at the top here. So delta t is equal to 1 over the sampling rate. Okay, so we're going to look at frequencies in the next workshop in a bit more detail, but let's just see what this means. So going back to our command window, Fs, or sampling rate, is equal to 1 over del t, and that is equal to 96. So recall that del t is time in days, the time interval between samples in days. So this means that Fs has units of 1 over days. So Fs 96 is equal to 96 means that there are 96 samples per day. So this is the rate at which this time series was sampled, 96 samples per day. Next, we should determine the sample length. Okay, so let's find out the maximum time minus the minimum time. So max of t minus min of t, and that gives us 365.9896 days again, okay, because the time axis is in days. You'll notice that's a little bit more than 365 days. That's because 2012 was actually a leap year, and it's not quite 366 because the last sample was actually 15 minutes before the full year, so it actually works as 15 minutes less than a full leap year length. So what this means in terms of our observable periods is that the longest period that we could observe is a full annual cycle. Okay, if there's any cycles that occur over, say, 3 or 5 years, then we will not be able to observe it within our current time series because it is not long enough. Okay, so the longest observable period we can see is an annual cycle, theoretically. Okay, now before we move on, if I just plot time, comma, h, and have a look at this. So time in days is if we want to work with days, because we're looking at time intervals and frequencies, it's much easier if we use units that are familiar rather than months. So we can see that this number is just a bit awkward to use because we're working from whenever day 000 was. So what we would like to do is actually start the time series at 0. So I suggest that we start it. We call that TD, so T in days, time in days, is equal to our time axis minus our starting day. Okay, so we just subtract that off so that our first, so we're starting from the first day in 2012, okay, rather than having it starting from that very long number. Okay, so we just subtract the first time index, and then we can try plotting that again. So plot TD, comma H. There we go, and you can see that we've got a sensible time axis at the bottom here and the tidal height in meters, and so it's all fine at the moment. Okay.